Hello to my second video. So this is a video on running the code. Previous video was how I made the data set. And so yeah, this is what this video is going to be about. We're mostly going to be focusing on the decoder, but I can go through the training code. And yeah, so let's get started. So we'll start from the bottom. And this is just for like the config file YML. So I'll skip that. We're main. Don't use this, but I do use WAN B. Here I build a model, and just to confirm that I am using GPT-2, I do save my runs with all the arguments and model architecture. So let's do this one, and yeah, GPT-2 to 256.8.12. So that's just confirming that I do use the GPT-2. Yeah, for all these, they're all GPT-2. GPT-2. Okay. And yeah, so let's go back to the training code. And we'll go to where the magic happens, which is this main train function. So, okay, so continuing walking through, optimizer is Atom, curriculum. I don't use curriculum, or there shouldn't be a need to use a curriculum anymore since I do have the pickle dataset. So this would be useful if I was creating the dataset live, but it's already made. So let's see, what is this? So this is loading, resuming training. So I don't really resume training, so not needed. MDIMS. MDIMS should not be necessary since I don't really use data sampler or task sampler. I guess the only thing I use task sampler for is just to know what loss function I use, but I only use mean squared error, so I could honestly just take that out and just hard code mean squared error. B size is 64, which is dependent on my config file. Right, 64. Here I have 85, so this is the max sequence length, so this should allow 85 states, which is 8.5 seconds worth if dt 0.1. Starting from 1 point to 85, but once again, I don't really need this since I'm reading off the pickle dataset, and yeah, dimensions doesn't increase. Saving every 250 steps, and learning rate 0.0001, and I continue on. So I don't really use any of this or this, but TQDM's just a nice fancy progress bar that I like to use, or that's amazing to use. Here is the directory for my training dataset, which is the corrected state pickles. And in the previous video, when talking about data, the corrected state pickles is inverted pendulum stabilizing sequence with no temporary energy increase anywhere. This is not needed either because I'm just reading off the pickles. Once pickles is done, or I reach none, then I just break. Pretty sure that's what it was. Here I'm pre-allocating a list to 40,000, and the reason, what was the reason? And the reason for this actually was I was testing out many loss functions while I was creating the pickle dataset, and so it was taking a long time, and I still wanted to test some things out. So I pre-allocated it to 40,000. So once, let's say I've had only 10,000 pickle files, and it takes like 10 hours to train. And after those 10,000 are done, once I reach a none spot or something empty, then I'll recheck again to see if anything was added. And it should, some of the logic of that should be down below, I believe. But yeah, I've just pre-allocated that. And here is just reading the data. Yeah, it's just reading the data. So yeah, loading the pickle, putting it into the array, and you're just printing every 499 when remainder 0 for 499. And I did 499 because at every 100 there's a curveball, talked about in the previous video. So I did 499 because I didn't want to see the curveballs. And yeah, so let's see, continuing on. So now this is where I'm iterating through the whole 40,000 pickle data set. And yeah, just reading it off. Here's the logic. Where does that end? You don't need to. Yeah, this is the logic here. So this was when, I was still adding to my pickle data set, and I was testing out different loss functions. So this here would check once validation. Which one was the last one? Param validation. Yeah, it would check with open. Yeah. So it would be checking that, and if it's empty, then just break. So that's what that was doing. But if there is some new data, then reload it. And yeah, I don't need that anymore. Data sampler, task sampler. Yeah, I don't use any of this. This was in the original repository. I just left it just because I didn't want to break anything, but honestly, this is not needed. I couldn't even show you that this should be empty. Ends up being empty, but okay, continuing on. Task sampler. This is the only thing I even use task sampler for, is just to get the loss function, which I could just hard code it because all I do is mean squared error. And yeah, I could also show that as well. Why I just put control values as y, as this was not even needed, but it is what it is. And here is my training step. And before we continue on, I want to show what this loss function is. So we'll do, I think I should have a team of 0. Okay, and I need to test for an hour. Yeah. Okay, and then I'll just train just to show, and I'll put it right here. Import didd.setTrace, and yeah, what was the function? Okay, so I don't think I'll be able to see this just because it's an. Oh. Okay, that's 40,000. I don't want to load all those. It'll take a while, so let's do 400 for now. Oh, also, let's take out this YMP. Don't need YMP right now. And I believe that should be it. Yeah. Okay. So now we can run it. Okay, so we're in line 252. So here, and so we'll just see what. Honestly, I can even show this. This should be empty. Yep. This is empty as well. And then, what is loss function? Don't think we'll be able to see it. Function mean squared error. Yeah, so it's just a function mean squared error. What's the command? You can do something like code. Oh, God. It's 2 underscores. Okay, so yeah, so it gives me what the file is. So yeah, so that's what the loss function is. I could have just hard coded it, and this is just lazy writing, programming, because when I added all these new loss functions, I would just comment this out and then uncomment this because they're all named the mean squared error, which yeah, it's just laziness. Yeah, this is MSLE, this is normalized MSE, And just because I think it's dependent on the task, so linear regression use the MSE, that's why the loss function is mean squared error, so I just didn't want to break it. And yeah, Gaussian, I don't really need it for training since I'm already using a pickle data set, but yes, it still works. Nothing breaks. It runs as intended. And before we go into the training step, go into base loss. I don't use base loss. I don't look at it. I just left it there. The only things I look at is overall loss, validation loss, and parameter validation loss. And curriculum update, don't really need it. What is this? Okay, and this is just saving the model. So it saves every 250. And we'll go to train step now. And yeah, optimizer 0 grad. This is where I run inference. So I pass XS and YS. And we'll go more into that and how the model interweaves X and Y. Loss function I already said was mean squared error. And here is where I apply the Lyapunov. So here across the whole batch, get all thetas, and then for this one, get all theta dots, and then just pass that into this function, where this is the partial derivative of the Lyapunov function with respect to the with respect to theta times velocity, and then plus partial derivative of the Lyapunov function with respect to velocity times acceleration, and that will show if there's any potential energy increase. If there is, then I add a penalty, and I even add this lambda coefficient constant times 100, which I tested out 10, 1, and 100 seems to do good. And even though this is 3 dimensions, this logic works. And also, even for mean squared error, this little piece of just this much line works for 3 dimensions because these are PyTorch tensors, so element-wise operations are being applied independently for each element in the tensor across the whole batch. So it's just a characteristic of the PyTorch tensor, and I did confirm it by doing a very smaller batch and did the math, and yeah, worked out the same as intended. And I think that should be it. So I add loss with Lyapunov, same for output and output val 2. Here I am just saving some results to text file, dumping the YML arguments into the text file as well. And then yeah, just updating the parameters and returning the loss so I could put it back into the YMB. And so now we're gonna look at the decoder, which I'll show again. Okay, so now we're gonna look at the decoder. And okay, so now we're gonna be looking at the decoder. Okay, okay, so now we are going to be looking at the decoder, and for the decoder, it's going to be on this model.py, and I want to bring up the PowerPoint just so I could show you what it was. So this is the decoder. There's a decoder here, and so I'm giving the model the x and the expected y, the x and the expected y, and so on. It predicts y for each of these, but I'm only keeping this one. Also, in this case, y is u, model's predicting u, just not to be confused. And so the whole premise of this is when I predict on this one for u, it's able to look at the previous, and so uh, we put the uh, expected answer here, so it's able to see like what we were expecting, and yeah, so it's only able to see history and not future. So that's the whole point of the decoder, and we're going to prove that in this video. And so let's go to the model using the transformer model, and these are the attributes of it, and this is the combine. So in this so yeah, it combines x's and y's, I guess. So this was what the original repository had, but you could go over it a little. Okay. So what this is doing is trying to match the shape of XSB, which is needed to stack. So here you stack it, and originally this is already 3 dimensions. Here you're stacking XB with YSB, and you're also adding actually another dimension here. So this should be 4 dimensions. And here view, so it seems like you're flattening it. Yeah, there's some flattening happening, and by using view with the flattening, it's interweaving the xb and the y, and so you have xy, or xu, 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 and that's what you return here. So yeah, this turns it 4D flattened to 3D, and that's what ZS is. And yeah, let's show that with numbers. So let's go back to model, and so here we are, and I am going to okay, add import IPDB set trace here, and gonna be running this Go Python train, and also have this empty Google Docs to write some of these numbers easier, since with Teamlex it's kind of annoying scrolling. So first we'll print out x, the shape of xb, which is 6412, which is expected, and then shape of ys 641, and then shape of zs should be 6422, since you are combining these and it needs to be the same shape. So I believe zeros was added. Yeah, torch zeros was added. So it should be 6422, and it is. And so let's show it with numbers. Let's actually just see the first one. So this is x0, this is y0, and then this is z0. Oh, but actually, let's do something else. Let's do 4,000. Let's also, I wanted to have at least a minimum of like 6 points to I equals 290. Okay, and let's rerun that again. So see, it's increasing 3, 4, 5. Okay, so let's do the shapes again. Shapes. Okay, so this one's 6, and then it should be 64, 12, 2, and it is. So let's just get these. So x0, y0, and then cs 0. And let's oh, why is it being weird? Okay, so let's copy. So let's copy from here. Oh, sorry, it's taking a while. Okay, we here, paste it, and we'll look over it after we do some experiments. Do CS here. And let's also keep on going. So we are in line 130. Okay, so let's keep going till we hit predictions. Output predictions. So predictions should also give 12, since there were 12 vectors in total. It's also predicting on the y, so x, y's. And yeah, that's what it is. And let's just see the first one. So this is the first one. Let's copy it and post it here. And now so this is what it's returning. So we can just print it here. Oh, we'll do yeah, so this should be getting every other one. So we'll just do x equals this, and we'll do x0. Okay, so this is the first one. So this is what output's going. Or this is what we're parsing, right? We're only parsing the every other. We don't care about getting these y predictions, just the predictions done on x. I'll do here. And so just to test out the decoder, we're gonna isolate, or actually we could look at this real quick. We'll look at this real quick. And so we have x, y, and so with ZS, it's interweaving x's and y's. So here we have the first x, which is this one, and then the first y following that, and then the next x here, 0.4258, 0.42, and the next one is negative 7.581. Yep, so it's xy, 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 and it ends on y, which is negative 0.552, and it's done here. And so prediction, the model is predicting on each vector, so make a prediction on that one, and then the next one, and so 12 predictions, right? And for what we want, we just want the predictions done on the x's. So the first one's the x, so we keep 0. This one, 288, and then we don't keep, it still makes a prediction on the y, but we don't keep it since we don't use it for our loss. But so we just see the next one, which is 0.4258, and it gives this one, and so yeah, it keeps on doing that, so it just gets every other, and this is y, and so x, yeah. And so just to see if the decoder is working, if it's only looking at history, we should isolate one of these vectors, which we should probably isolate this one. I think that's a good enough number. And so let's make this red. Oh, not that one. Let's make this red. So 0.3. This is 1, 2, 3, 4, 5, 6, 7. Then 1, 2, 3, 4, 5, 6, 7. Okay. So this one. And then there's 0.5. I don't think I need to highlight this much, but it's fine. Okay. So yeah, 1, 2, 3, 4, 5, 6, 7. That one. This is a prediction 1, 2, 3, 4, 5, 6, 7, which is that one. Okay. And so all we gotta do now is do some slicing. So if it's so we're keeping the first so we're keeping the first 7. To do that, just slice, slice, after the combine. So it's 3 dimensions, then it's okay. So I believe that should be it. Actually, I could even double check. Oh, back to equals that. And yeah, okay, so it is that. So let's rerun this. And I actually don't want the trace here. Just do the trace on here. Okay, so let's rerun this. Okay, so we have, let's check out shape, so it shouldn't be 12. Okay, so that's correct, and let's just double check. So yeah, so we destroyed or took out all the future ones, and so it should still be getting the same number that we had, and we'll recheck all the numbers again. So let me just copy this. And put it down here for the second one. I'll color this different color, blue. And now we'll do prediction 0. Okay, so this is prediction 0. And honestly, we just go up the stack and just print out the output 0 instead of doing the slicing. And so here we are. We'll do output 0. I guess I'll change that to output 0 since since it's the same thing, just so I won't get confused. And okay, so that's that. And then this was getting the first 7, so let's just keep the last 6 now. And so it should be 6 now. I wish I could check, but I actually overwrit the. I think that should be fine. Yeah. Okay, so let's rerun this one more time, just double check everything. Okay, so let's do ZS 0. So the first one should be that number we were looking at. I believe it was 0.30 or something like that. And yeah, it was this one. So yeah, so now this is keeping the last 6. And I'll copy that, put it in my file. This is a different color, indicating it's orange. Okay, so then we'll do prediction 0. Okay. And then for the last one, I'll once again go up the stack and just do next, and then just put output 0. A lot quicker. And yeah, okay, so now we're able to look at this. So we're done with that. And so we highlighted the 7th one, so 1, 2, 3. So this one was being done, 0.3012. This is 0.3012. So let's highlight that to red. And so that one's the last one being done here. And then here, 0.3 is the first one. And so is the first prediction, which is, I guess, this. I want to highlight that. and this one's the last one. Okay, so let's look at this. So hopefully actually you guys can see. Okay, so originally 0.3012 with previous and future sequences being given got an output of 0.5467. And so for the next one, I removed all the future sequences after that one and see if it was affecting that prediction. So it should still, the decoder should only look at the history. So this number should still be true even after I remove the first ones. I mean the last six or five. 1, 2, 3, 4, 5. And yeah, so let's look at that second one. So now it's the last one, and it was 0.5467. So once I make prediction on that, it's still 0.5467. So this shows that including the other sequences ahead of it does not affect it. And so now we're going to test um, what if we remove the previous and just keep the first? Does the previous even affect that one? So we already concluded that the ones after it don't affect that prediction, but do the previous one affect it? Um, so it's this test. So now 0.3012 is first, and the prediction is now 0.5827, and so it's different from the other two that we got. So when we remove the previous ones, it does affect it. So this concludes that the decoder, the autoregression model, looks at previous states and not the future states. So we can effectively give it this whole thing, and it'll be learning from previous in context. So once it makes a prediction, it's able to look back at all these, and it doesn't look at these. So that's why we can use the decoder to emulate this in context learning of models. And yeah, that should be it with the code. Um, it's just training. Yeah, just return after that. Go back to the train. Um, Also, I did add like a lot of my Liapana or a lot of my loss is different, but they're all named mean squared errors. Just so I won't lose track, I do name these differently. So if you pay attention, so if you see my runs, I put the loss function that I'm using. So log cosh, log scales, all that, and yeah, I'll make it much more efficient than uncommenting and commenting, but just for now and for like just to get the ball rolling. This is what I had done. So there's a lot of code that I don't use that's still being implemented here. Um, but yeah, this is how I was running the model, and it does seem to follow the in context learning. And so next video is going to be on inferencing, and yeah, stay tuned. Thank you.